Welcome to the HeatWise tutorial on the ASHRAE 62.1 ventilation rate procedure. In this video, I'll be going over how to do proper ventilation calculations, specifically going through the ventilation rate procedure as described in ASHRAE 62.1. This will be based on the 2022 edition of the standard, although there is a more recent one now available. Most jurisdictions are not yet enforcing the 2025 edition, so this will be focusing on 2022. So before we get started, I'll just give a brief description of what this is. So ASHRAE 62.1 is the standard that is enforced in most jurisdictions in North America as well as other parts of the world for how to properly calculate and provide the necessary outdoor air to a space or a system to maintain good indoor air quality. This is to prevent buildup of contaminants like CO2 or volatile organic compounds. So we have various things that can create odors or health hazards within your space where the best way to deal with it is to just dilute the air with fresh outdoor air. And this helps make sure the oxygen content is at its proper levels, keeps down CO2 and volatile organic compounds, as well as anything else that might be in the space. So the ventilation required in a system is calculated in two different paths. There's the ventilation required per space, and there's the ventilation required at the system level intake. Now, in ASHRAE 62.1, there are three different types of systems that are described. So the first is the single zone system. So this would be a space where you have an air handling unit, and it is serving supply air to that space, taking return air from the space, and then just brings in some outdoor air to condition the space properly with the ventilation it needs. So the second type of system is where you have what is called a dedicated outdoor air system, DOAS or DOAS. This is a 100% outdoor air system, so it just brings in pure outdoor air and delivers it to each space individually. So a basic schematic would look like this, where you have a bunch of different zones and you have your DOAS unit. The DOAS unit is just supplying outdoor air to each space individually, and this air is, of course, 100% outdoor air. The third kind of system is a multi-zone recirculating system. So similar to a DOAS system, it is supplying air to a bunch of different zones, each with their own unique outdoor air requirement. The difference here is that it's not supplying 100% outdoor air. It is recirculating air from each zone. So it supplies air to the zones and it pulls return air from all zones, mixes that return air with outdoor air, and then resupplies that supply air to the zones. So the supply air is some fraction of outdoor air, so it might be 20% or 50%, but it is not the pure outdoor air that the DOAS system is supplying. And that makes it a little bit more complicated to make sure that all systems or all zones are getting their outdoor air requirement met. So now we can move on to the actual calculations involved in the ventilation rate procedure. There are two main outcomes that we actually want to determine. That is the zone outdoor airflow. So that's the outdoor airflow required for every zone in the system. And then there's the outdoor air intake value, and that is the net outdoor air required at the intake of the air handling unit. The zone outdoor airflow is going to be the same for any type of system, so whether it's single zone recirculating, DOAS system, or a multi-zone recirculating system, the zone outdoor airflow will always be calculated the same way. What's different between the systems is the ventilation intake value. The zone outdoor airflow is abbreviated with OZ, so it's V sub OZ, and the outdoor air intake value for the air handling unit is abbreviated by OT, so that's VOT. So diving into the calculations now, we'll start with the zone outdoor airflow calculations. These will be the same for any system type, and the zone outdoor airflow has to be calculated for every single zone in your system. So the high-level equation for VOZ is simply VOZ equals VBZ over EZ. So naturally, the next question would be, what are these values and how do you determine them? So VBZ is equal to the breathing zone ventilation rate, and EZ is the ventilation effectiveness for the zone. So we'll start with the calculation for VBZ. So VBZ is equal to RA, which is the outdoor air rate by area for the zone, multiplied by AZ, the zone floor area, plus RP, which is the outdoor air rate per person for the zone, multiplied by PZ, which is the zone population. So RA and RP are both rates that can be looked up from tables in the ASHRAE 62.1 standard. AZ and PZ are both dependent on the characteristics of the zone. So AZ is just simply the floor area of the zone, and PZ is the number of occupants that would be expected in the zone. So AZ and PZ can both be determined from the floor plan. So AZ can just be measured simply for each room, and PZ is usually determined by the number of seats in a room or some other way of estimating the maximum occupancy of the room. If it's difficult to do, it can also be taken from ASHRAE 62.1 values. So now all we need to do is determine our RA, RP, and our EZ values, and all of those can be taken from the ASHRAE 62.1 standard. So now we can go take a look at the standard and find those values. So I'm looking here at the online preview of the ASHRAE 62.1 standard, which is available through the website, so you can access this free preview. And you'll see that there's a number of tables within the standard, and we're looking for table 6-1. That will give us the RP and RA values, both listed in columns here for a whole bunch of different space types. So for whatever space our particular zone corresponds to, or whatever one best describes it, we can look up the values for RA and RP. And you'll also notice that there is an additional column for occupant density, so it gives the number of people per 1,000 square feet. That's an important value for when you don't know the occupants, the number of occupants in your space. So a good example is like the sales floor of a grocery store. It would be very hard to determine how many people would be in there, so you could take a default occupancy value and use your floor area to try to estimate the occupancy of that sales floor. Another example would be like a shopping mall where in the hallways people might be walking around, but it's very difficult to say how many. A place where you would not want to use one is, for example, a movie theater, because a movie theater would have a set number of seats. So you would just count the number of seats, and that would be your occupancy for the theater. So once we've obtained our RA and our RP values, we can scroll down to table 6-4, and that's where we'll find our EZ value, the zone air distribution effectiveness, and we can pick the value for EZ that corresponds to how air is going to be distributed within our zone. So you can see from these options, it is dependent on the kind of air that is being supplied, as well as how it's being supplied, from the ceiling or from the floor or elsewhere, and where it's being returned. So once we can determine that, then we can find our EZ value, and then we have all three values that we need for now, and we can plug them into our equations. So once we've obtained our RA, RP, and EZ values from our ASHRAE 62.1 standard, we now have the EZ value and what's necessary to calculate the VBZ value, which are both needed to calculate the VOZ value. And once we've calculated our VOZ for every zone in our system, we can then move on to calculating the VOT value. And this is where things get a little bit more complicated, because the VOT value calculations depend on the type of system that we're using. So we'll start with a single zone recirculating system because it's the easiest. So in a single zone recirculating system, there's only one zone, so you only calculate VOZ once, and VOT is just simply equal to the VOZ that we just calculated. That's because there's nothing else happening, there's no dilution, there's no mixing with other spaces. It just simply requires the zone outdoor airflow that we just calculated to be brought into the air handling unit that will be dedicated to that single zone. The next system type that we'll look at is the DOAS system, dedicated outdoor air system. So for that system type, the VOT value is equal to the sum of each VOZ value that we just calculated. So once you calculate the VOZ value for every single zone in your system, you just add up those values, and that is our VOT for a DOAS system. And this intuitively makes sense because the air handling unit is not handling anything other than the outdoor air that it's being that's providing to each zone. So it just provides the VOZ value to each individual zone. So each zone gets its VOZ, and then when you add up the total airflow in that system, it will equal some ultimate value, which is going to be the VOT because it's not taking in anything other than fresh air. So now we'll move on to the third and final system, which is a multi-zone recirculating system. And in this kind of system, there's a number of steps to get to the VOT value. So we'll start with the highest level equation, where VOT is equal to VOU over EV. And naturally, the next questions would be, what are these two values, and how do we calculate them? So the VOU is the uncorrected outdoor air value, and EV is the system ventilation efficiency. So VOU is probably the only equation throughout this process that actually has kind of an ugly looking equation. So VOU is equal to D, which is diversity, multiplied by the sum of RP times PZ for each zone I, plus the sum of AZ times RA for each zone I within the system. So for each zone, we take our AZ and RA value, multiply them together, and then add up all those values. And we take our RP and PZ values and multiply them together for each zone, and then add up all those values and multiply those by the diversity factor D, and then we would add these final results together to get our VOU value. So we've now introduced this new variable of diversity factor. So diversity is what we use to account for the fact that we might be double counting occupants when doing our calculation. So if you think about a typical example like an office, where you might have a bunch of offices and cubicles, and then you might have a boardroom as well. Each of those spaces would have its maximum occupancy, including the boardroom, but the people that would be in the boardroom are the same people that would be in the offices and cubicles. So they would leave those spaces, come to the boardroom, and then they would leave the boardroom and go back to their other space. So it's the same occupants, but they would be double counted if we were not using this diversity factor. And luckily, the calculation of the diversity factor is quite simple. It's the system population, PS, over the sum of all zone occupancies, PZ, for each zone. So you take PS divided by the sum of all PZ, and that is your diversity factor. So since we saw earlier how to find the RP, PZ, RA, and AZ values from doing our zone outdoor airflow calculations, and we now know how to get our diversity factor D, the only value that we don't have is the EV value. The calculation of the system ventilation efficiency, EV, is only dependent on the diversity factor. And how we calculate EV is dependent on whether or not the diversity factor is above or below 0.6. So if the diversity factor is less than 0.60, we get 0.88 times D plus 0.22. Otherwise, if D is greater than or equal to 0.60, then we just say EV is equal to 0.75. And an easier way, or at least a more compact way of writing this equation would be to state EV is equal to the minimum of 0.75 or 0.88 times D plus 0.22. And this makes it a little bit easier to program into something like Microsoft Excel if that's where you're doing your calculations, rather than having this conditional calculation procedure. But either way will give you the same value. So once we've calculated EV, we now have everything we need for the entire multi-zone recirculating system outdoor air intake value. So we have our EV that we can plug into our VOT equation, and we have our VOU because we've calculated the D value. So we now have the procedure for calculating outdoor air intake value VOT for every kind of system. So before we move on to the final part of this video, which is a full example of a multi-zone recirculating system, there is one variable left to discuss, and that is the VPZ minimum value. So VPZ is the abbreviation for the primary zone airflow. So primary zone airflow is just the airflow supplied from an air handling unit needed to condition the space, so either heating or cooling airflow. And this is completely regardless of outdoor air content. It's just the airflow that needs to be provided to a space for conditioning. Our zone outdoor airflow calculations in a multi-zone recirculating system require a minimum primary airflow, and that's to ensure that in cases where a zone might not have much need for conditioning, either heating or cooling, it still needs a certain amount of air from the air handling unit to make sure that it is getting the outdoor air that it needs to have. So luckily the equation for VPZ minimum is quite simple. It's just 1.5 times the VOZ value, and that is applied to every space within your system. So if we take a simple example like the one in the diagram here, we have an air handling unit providing a mixture of return air and outdoor air to every space, and so the supply air is only partially outdoor air. So with every zone there will be an associated primary airflow, the VPZ value. So VPZ minimum would just be 1.5 times the VOZ value for each zone, and that's the minimum that we have to provide from the air handling unit to the zone. And now I'll finish this video off with a quick example of a multi-zone recirculating system. So we'll go to a spreadsheet here to look at the list of zones within our example. So you can see here we've got a bunch of offices, offices 1 through 6, and then some cubicles and a lunchroom and a boardroom. So I've already populated the table with the RA and RP values. So for each zone here, it's just 0.06 CFM per square foot of area and 5 CFM per person. So that'll be the same for every zone here. That's just how it happened to work out. It could have easily been different for different zones. But then I've also populated the area and the estimated occupancy for every zone within this table. So all of these values you would have gotten from the ASHRAE 62.1 standard and the floor plans that you're using for your calculations. So I've just populated them here, and you can see we've got a VBZ value. And if I click into the cell, you can see that the equation that's been programmed into here is the equation that we had written earlier for VBZ. So you do this for every zone and just simply drag it down and you have your VBZ for every zone. And after the VBZ value, you'll notice that we have two EZ values, the EZ cooling and EZ heating. And the reason for that is because the EZ value can depend on whether or not you're supplying warm or cool air. So in the ASHRAE 62.1 standard, if we go down to table 6-4, you'll see that there are different values for the EZ value depending on if we have heating or cooling happening. So if we have a system that is doing both heating and cooling, for example a packaged rooftop unit system, then what we're going to see is two potential situations, one where we're supplying warm air out of the duct system and one where we're supplying cool air. So we want to include both values because just in case one results in a higher VOZ value than the other. So if we're using one duct system but have two potential situations, we want to make sure that we're getting the proper outdoor airflow, which means we're going to have to meet the more strict situations if we're not able to modulate outdoor air, which in this case we'll assume we can't. So what we do is look at both of these values and take the most conservative calculation. So you can see in the formula here we're using the minimum value between the two EZ values, and that's because this is the zone air distribution effectiveness. So the least effective method of distributing air is going to give us the highest outdoor airflow value, so that's the one we're going to use. So in this formula we use minimum of heating or cooling EZ value, and we use that in our formula for VOZ. And the final column of calculations here before we get into the VOT calculations is the VPZ minimum. So of course this is just 1.5 times our VOZ value, and that is applied to every space. So you can see here the cubicles, for example, need an airflow of nearly 300 CFM, regardless of any conditioning requirements. Just to meet the outdoor air needs, we have to provide a primary airflow of at least 296 CFM to the cubicles. So now moving on to the calculations needed for our VOT value, the intake ventilation to the air handling unit. We'll start with our PS, so that's our system population. So if we count up our spaces, and we can make a reasonable estimate here that the lunchroom and the boardroom are not going to be regularly occupied, and the people that are going to be occupying those rooms are going to be the same people that would be in the cubicles and the offices. So the cubicles and the offices are the only permanent employee sitting locations, and when they leave those places, they might go to the lunchroom or the boardroom or elsewhere. So our PS in this case would be just the population of the cubicles plus the populations of each office. So we'll just program this with a simple formula, taking the sum of the occupancies for each of these spaces, and then determining our sum of PZ values. That's just the sum of all occupancies, including the lunchroom and boardroom. So you can see we've got 22 and 54 as our two values here. So using those, we can calculate our diversity, and that calculation gives us a diversity factor of 0.407. So once our diversity is calculated, we can do our system ventilation efficiency. So we'll program our equation here that you would have seen before, where EV is the minimum of 0.75 and 0.88 times D plus 0.22. And that gives us an EV value of 0.578. So the next step is to calculate our VOU value, the uncorrected outdoor air. So that is D multiplied by the sum for each zone of RP times the occupancy. So for this equation, we'll use sum product formula in Excel. So the sum product takes two lists of numbers and multiplies the first number by the first number and the second number by the second number, and so on. So we give it two lists, the list of RP values and the list of occupancy values, and then it will give us the sum of each of these multiplied together, and then ultimately multiplied by our D value, and then we add in the sum product of our RA values and area values for each zone. And I'll just show you what this formula looked like written out again. It looks a little bit different in Excel, but I assure you these are the same things. So this gave us a VOU value of 302 CFM. So our last step is to calculate our VOT value, and that is just the VOU value divided by EV. And ultimately we get a VOT value of 522 CFM. So that is a full example going through a multi-zone recirculating system where we have a bunch of different rooms in an office type situation. We get our VOZ values and ultimately our VPZ minimum values, and then we go through the calculations to obtain our VOT value, which will be needed at our air handling unit intake. So that is it for this HeatWise tutorial on the ventilation rate procedure. We'll see you in the next video.